Okay, here's my review for the STEM activity that I chose, which is called Shapes of Strength. In the original activity, students will work collaboratively to create the strongest shape or structure possible. The link is below, and I'll also attach a link into the submission that I put onto our web page. The activity summary is this. In the activity, the students investigate the strength of shapes and utilize their discoveries to make a structure that's capable of supporting weights many times greater than the materials of the structure. There is a period of reflection, reconstruction, and retesting that keeps the activity interesting and moving forward. There are certain limitations put forth on the activity so that children know the parameters and also have an appropriate challenge. So the limitations are that the structures have to be able to hold a book 1.5 to 2 inches off the ground. They will have 1 minute to decide how to build the structures, 8 minutes to build, and then 2 minutes to actually test them. Materials supplied, each team gets 10 pieces of paper, 10 straws, 1 roll of masking tape, and 10 paper clips. And there are also other materials available like scissors to help them cut if they need to. After the first trial is over, students will have a chance to improve, revise, or even scrap the model that they've been working with. In terms of STEM alignment, it aligns just about perfectly with the aspects of STEM that we're looking for. Will they be asking questions and defining problems? Well, absolutely. The question that is asked initially turns into many other questions that they generate themselves. It starts off by, asking them, what is the strongest shape or structure you can build? And then they're bound to ask themselves questions like, well, which material could make the strongest shape? Or how could I manipulate the materials to make them stronger than they are in their current form? So they have a chance to ask questions and define problems. Plan and carry out investigations. Of course, that's exactly what they're doing in the activity. Analyze and interpret data in as much as you could say the observation of what happens would be data. You could say that they're definitely analyzing what happened and interpreting what happened. Using mathematical thinking. Initially, I thought maybe that wasn't really present, but then it occurred to me that basically what we're working with here is geometry, and that certainly is a field or a subset of mathematical thinking. Another category of STEM elements that we should think about are the following. Constructing explanations. Well, after the second trial is completed, students are to present their results and their findings to their classmates. So, of course, they will be constructing explanations for what happened, either why it worked well or why it went poorly. So that element is taken care of. Engaging in argument based on results and evidence. Well, they'll certainly have opportunities to discuss in the second round of their project, and then also after the second round when they're planning to prepare their presentations. They're going to be discussing and trying to come up with explanations, and there might be some argument about which shape is strongest and why. And then communicating the information, they absolutely will be doing that when they present their projects to one another. So I would say that this project meets every single aspect of STEM that we're looking for. The next question is, how does it match up with the inquiry expectations? And again, I would say this matches up pretty much spot on, perfectly. There are scientifically oriented questions involved in this. Again, which shape is strongest? Why is it strongest? What material could we use to make the strongest shape? priority is given to evidence when responding to questions. Well, certainly all of the questions that they're asking would have evidence to refer back to in terms of deciding what is strongest, what shape is strongest, what material serves the purpose best. So they will certainly be using that aspect of inquiry. Formulation of explanations and evidence is clearly there, and again, when they go to present or when they go to revise their designs, they're going to need to refer to the evidence of the previous attempts and then also work with explanations for why the events happened as they did. Explanations are connected to scientific knowledge. This becomes during an important part during the revision stage, because in between the first trial and the second trial, students will be given some resources or encouraged to find resources that they can use, not necessarily to reverse engineer, but basically to look at architectural designs and structural designs and try to notice shapes and decide why those shapes were used and why they're strong. So there's definitely going to be scientific knowledge being integrated into their explanations after they do the research. Learners communicate and justify explanations. Well, they absolutely will be doing that at the end of the project and also throughout the project, where they must communicate with each other and then, again, justify their explanations. After they have some content knowledge from studying other designs, they'll be able to justify any position they have, whether a kid thinks that a parallelogram might be the strongest design, or a square or a triangle. They have plenty of examples to look at in architecture and engineering to compare. So the activity, I'm disappointed I wasn't able to find time to do this with my students. Today was our last day, and it was definitely, it was a half day. The last 2 days were half days, and it was certainly hectic getting everything finished for the year. But I then elected to do this project at home. So model number 1, recognizing that there was only 1 minute to plan what I was going to build, I came up with a quick idea of columns. So I took straws, I cut them into equal lengths, roughly, and I used the tape that I had. In this case, it was duct tape, so it was a little different than the masking tape that they said you're supposed to use. I'm not really sure if the tensile strength of the two materials is that different that it would matter in this experiment. So I guess I'm asking my own scientifically based question now: which material is stronger, masking tape or duct tape? The columns were distributed evenly in a rectangular pattern underneath the book. So you can see in the first picture are the columns that I made, and then the second picture, the columns being put to use, holding up the weight of a rather thick book. My results. The columns supported a considerable amount of weight. You can see again in the first and second picture, managed to stack 4 fairly heavy books on top for their strength test. So then it was time to consider revising my project. And the constraints of time that this project presents students with made me basically limit my solution or my way to try and improve the design significantly. There's not very much time to plan out exactly what you're going to do, and there's not very much time to actually execute it. So what I decided to do was go with, in Model 2, the thought, well, if 4 were good, then surely more would be better. Or so the thinking went. So I made 2 more sets of columns thinking, hey, when we distribute the weight over them, there'll be less pressure spread out on each one, and they'll be able to take more weight. Well, it turns out that more was actually less in this case, because the 2 extra, and I might add, poorly cut columns were the undoing of the plan. So I set the books on the columns, and before long, some of my new columns, I believe, started to slip because the cuts were somewhat angular. Instead of being flush with the surface that they were resting on, they were at angles, and then when any significant weight was applied to them, they would slip. And of course, when they would slip, then the weight would get redistributed, and the other one would slip, and before you know it, the whole thing collapsed. So model number 2 was a total flop, but the point is there's always something to be learned from even failures. So there were things that I learned from this as well. In terms of modifications for the students, and I've already alluded very strongly to this, based on my own attempt at the activity, I think that the planning and building times are far too short for elementary students, really students of any age probably. And I would consider giving literally 5 times as much time for planning and construction. It just gives kids a chance to plan a little more thoughtfully and certainly build more solidly. And then the other thing is there is a great deal to be learned from the activity and the challenges that it presents. I like the activity. I think it's very worthwhile, and kids would get a lot out of it.